Hi, I'm Brianna Dolan, and I'm on Team B15 with Alexa Batson, Riley Dowdle, Louis Finney, and Cindy Son, and our project is a low-cost battery-powered ventilator. The goal of our project was to design, test, and build a low-cost battery-powered ventilator with a budget of $1,500 in hopes of lowering the child mortality rate resulting from respiratory illness. Why are we doing this project? What is the motivation behind it? Well, the leading cause of death in children under the age of 5 is respiratory illness. This is in part because medical facilities in developing countries lack funding, limiting the number of ventilators there is per facility. In more rural areas, there is also problems pertaining to electrification and patient transportation from rural clinics to larger medical facilities. The current solution to all three of these problems is to have patient family members and medical staff take shifts manually ventilating the patient with an ambulatory bag, a very physically demanding task. The top 5 customer needs for the device are that it is reliable, low cost, easy to use, safe, and convenient. For reliability, the device needed to be able to consistently and accurately output desired pressure and airflow values. For low cost, the goal was to keep the per unit cost around $800. To make the device easy to use, the UI needed to be intuitive and helpful for medical staff. To achieve this goal, we collaborated with 2 students from Milwaukee Institute of Art and Design. To ensure the device was safe for patients, it needed to have a safety release valve and an alarm system to stop and alert medical staff in instances of error. And lastly, the device needed to be lightweight, portable, and clearly display all pertinent patient information. Since this is a legacy project, past teams have worked on developing a solution to the same problems we now face. Previous teams designed their airflow mechanism to be a mechanical piston. With this design, there is the presence of friction that slightly decreases the overall efficiency of the device and drains the battery more quickly. Our design is an electromechanical airflow mechanism. Our mechanism is made up of a constantly running pump that connects to a solenoid valve that, when closed, stops air from reaching the patient as they passively exhale, and when open, allows the air to reach the patient as they inhale. We found that leaving the pump on and mediating the air with the solenoid valve would be more efficient than both the mechanical piston and having the pump turn on and off with the patient's breath cycle. The user interface here was designed in collaboration with MyEd students. All pertinent aspects of patient and device status are included on the main screen so that maneuvering through the UI is limited. Additionally, all related information is color coordinated and well labeled to ensure that it is intuitive, clear, and easy to use for medical staff.
In order to support our design and the customer requirements after conversing with students in Columbia, an outlet-powered system with a battery backup was chosen. This would provide greater flexibility to healthcare workers and medical staff that could use the product in a greater variety of situations. Some of the biggest components that would draw power from this system would be the screen, the Raspberry Pi, the solenoid valve, and the pump. These different components are going to have the most amount of current draw out of all the others. Some other components that we used were a variety of temperature, pressure, flow sensors, push button encoders, and fans. With all these components, we needed to take full advantage of all the Raspberry Pi GPIO pins in order to control all of them. The GPIO pins are digital, so they can either be set to on, off, or a PWM signal. Almost all of our components are digital only, with the exception of the pressure sensor, which is analog. So we used an AD converter in order to still have that be inputted into the Pi and read voltages coming out of it. All of these circuits have been simulated in multisim, and so even if we weren't able to test all of them in person, we still have reliable data that ensures we are confident in the design.
For the software aspect of our final design, we opted to use the coding language of C++ and Python. C++ is commonly used for medical devices, and Python is easily accessible via the web to have lots of resources for the Raspberry Pis. Using a multi-threaded approach, we outlined our software to have one major thread running continuously, with smaller worker threads coming in and out of the design to update different data values that the Raspberry Pi needs to control the various components. The Raspberry Pi is ultimately responsible for controlling all of the components in our design. It's accessing multiple data values to properly control the solenoid valve for breath patterns, obtaining temperature values, and CO2 sensor data to ensure that the patient is always safe. We also looked at other resources that would make our project easier that already exist on the web. Boost C++ is a library that is open source that has a lot of functionality, so we wouldn't have to reinvent the wheel. The Wiring Pi and the software PWM libraries also were available to us for the Raspberry Pi to access GPIO pins and special functionality of the Raspberry Pi pins, such as an I2C or a SPI bus. For our UI design, we were going to use a program known as Qt Creator that allows us to use signals and slots to correspond our C code to properly interface with the rest of the code. One of the essential scripts that we were writing was a way to control the PWM signal for the solenoid valve via software. This scripting would allow for different breath patterns to be available based on patient needs. In addition to these scripts, we were also looking at different individual component scripts so that as we built the device, we could incorporate components one by one, following a lean or agile software development plan.
The purpose of the mechanical design was to provide safe, reliable, and consistent airflow to a patient using constant pump flow. We achieved this with a 12-volt miniature diaphragm pump, which provides up to 5.5 liters per minute, enough to sustain a child under the age of 5. The final mechanical design involves the constant pump flow that provides air through a mechanical release valve, then solenoid valve, and then to the patient as displayed in the exploded SolidWorks view below. The mechanical release valve shall be set at a certain pressure and will open if that pressure is achieved as a safety mechanism to allow pressure and airflow to escape the system. The solenoid air valve will continuously open and close the airway to simulate inhale and exhale of breath. There are numerous female pipe T adapters connected to ensure ease of assembly and airtight connections between our 1/4-inch diameter tubes. Our senior design team has worked with MyEd students this semester to design a functional and aesthetically pleasing housing. We then developed the design in SolidWorks and 3D printed the housing. The internal components sit perfectly inside the plastic housing where they will be secured and protected to ensure reliable outputs to the patients. There are 2 holes, one on each side, for air intake to the pump and air output to the patient. There is a slot located in the back left for outlet plug accessibility and an on-off switch located in the back right. The back portion of the housing is detachable for easy access to the inside of the ventilator for maintenance and controls. 2 indentations are located on the bottom of the ventilator to place your hands for ease of transportation. Vents were also incorporated in each side of the housing to allow heat to escape and to ensure a safe environment for the internal components. The 3D printed housing was painted to highlight each external component's function. The large black space is where the LED screen will sit. The 2 blue buttons on the top right are designated for pressure controls. The 3 yellow buttons are designated for airflow controls. The orange button is for tidal volume controls. The red and green buttons are stop and start, and the gray buttons are for general purposes such as settings, parameters, language, and mute.
Hey, so we have a quick demonstration right now of what our product would look like as a proof of concept. So first, the actual setup is this. So we have a simulation of a patient's lungs here, where this balloon is going to be getting inflated and then deflated. Connected to that over on this side is a pump, which is going to be connected to the DC power supply. That pump is going to push air through here through this T valve and through to the patient's lungs. On the other side, we have a solenoid valve, and that's going to be controlled by the Raspberry Pi here. So it's going to go through a transistor amplifier circuit so that when that signal is on, it actually allows air to pass through here. So instead of going to the patient's lungs, it's going to be going out on this direction. You can see the code is up here, and I also have an oscilloscope measuring the input signal from the Raspberry Pi. So first we're going to be turning on the DC power supply. Fair warning, this does get pretty loud. So you can see it immediately starts to inflate. And if I start running the code over here, and after about 5 seconds, there it goes. So now the solenoid valve opens up, and after about another 5 seconds or so, it's going to close, and there it goes. And so now you can see the patient's lungs are inflating, and after another few seconds, it's going to deflate and inflate one more time. I don't know if you could tell, but you could hear the clicking coming from the solenoid valve when it was opening and closing. Thank you very much.
To verify our experimental design, we wanted to use a process that would allow us to test individual components before integrating them into the overall design, one component at a time. By following a lean or agile-based approach for both software as well as hardware and circuitry, we would be able to have an easier time debugging issues before moving that component to the overall design. In our test plans, we covered both individual component testing as well as use case scenarios that healthcare workers might face to have a better understanding of our ventilator. Due to COVID-19, however, we were unable to do a lot of our experimental verification that we were originally planning on doing. We've had limited access to resources for building the prototype, but we are very glad to have used a function generator, oscilloscope, and power source from the BioE and BioC lab to at least test a proof of concept. For our proof of concept testing, we were able to look at two main things that we wanted to focus on. The first being the Raspberry Pi CPU load handle and the software-controlled PWM signal ability. We were able to run command line arguments to test whether the CPU could handle such a large load being applied to the Raspberry Pi. We also wanted to verify that the GPIO pin's functionality of providing a strong enough signal to control the solenoid valve would be possible. We found that in our proof of concept testing, both of these tests passed.
Our team's budget was $1,500, and our goal for the total product cost was around $800 per unit. After compiling the component costs, labor costs, and total cost of the product, we have proven that our product is economically feasible. We found that the estimated total cost of the components was around $580 per unit. The estimated labor cost, assuming a $20 hour rate for assemblers, was about $4 per unit, and when taking into account the component, labor, and overhead costs, we determined that the total cost of the product would be around $642 per unit. This is about 20% less than our goal and about 28% less than the previous 2018 team, which was around $900. We are confident that our ventilator provides safe, reliable, and convenient outputs at a reasonable price.
In summary, our final ventilator prototype is proven to be technically feasible based on the results from the experimental verification and outline of our final design. As a result of our cost analysis, our prototype is 20% less than our budget of $1,500, and our cost per unit is less than that of previous years, proving that our prototype is economically feasible. Our prototype meets our customer needs through validation of our target specifications. And lastly, we were able to complete our prototype before May of 2020. Due to the conditions presented by the COVID-19 pandemic, our final ventilator prototype was unable to be completed. Majority of the experimental verification tests were unable to meet the target specifications due to a lack of resources and the inability to meet with the whole team for in-person work meetings. Instead, experimental testing procedures were written for each test with expected values. Future teams will be able to closely follow these procedures to conduct the testing necessary to verify that all the required target specifications have been met. A work instructions manual has also been created that outlines detailed instructions on how to assemble each component of the ventilator. These work instructions will be utilized by our project sponsor, Dr. Olson, and his team in El Salvador to build the final prototype over the summer of 2020. There are a number of recommended design changes that improve the overall performance of the ventilator. The shift in focus of this project is more on cost reduction, and reliance on battery power was found to not be of critical importance, since most urban areas in developing countries, where majority of these ventilators will be of use, have reliable power sources. Additionally, reducing the size of the chassis will also aid in cost reduction. According to the final SOLIDWORKS model, there is more space allotted in the final prototype, which can be further reduced to decrease the material costs. Lastly, it was determined during experimental testing that the current solenoid air valve must be changed to a proportional control valve. This design change was necessary to vary the rate of airflow depending on the patient's needs.